So today we're looking at isosceles triangles. We're also looking at equilateral triangles. Just to get some basic vocabulary out of the way, we're all in different places. Some of you will know this, some of you may not. But let's start from the beginning. Isosceles triangles are triangles with two congruent sides. And we have special names that we're going to use for these different pieces of an isosceles triangle. So here it is, and I've marked my congruent sides. Those congruent sides are called the legs of the triangle. And this side down here is called the base. So the one that isn't congruent is the base. The vertex angle is the one up here. And the base angles, I should say this better, the vertex angle is the included angle between the legs. And the base angles are the angles that touch the base. The base is the included side between those angles. So if I'm talking about the base angles, I'm talking about these two angles here. Okay, so just a little bit of vocabulary. Here's an isosceles triangle, and it doesn't really say. So I'm gonna say that these are the congruent sides of it. And let's see if we can find these little pieces here. So which is the vertex angle in this particular isosceles triangle? Ali? I'm looking for an angle, angle ABC? Yeah, angle ABC, and you could have also just said angle B. You're right, this one. So there's my vertex angle. Where is the base? Name the base of this isosceles triangle. Amy? Yep, segment AC. There's my base. What are the legs of this isosceles triangle? Ready? One person? What? Jack, what are the legs?
AB and BC.
Right, segments AB and BC. So these are legs. And then where are the base angles? What are the names of the base angles? Base angles. Abby? Yep. Right, so these are my base angles. And just to kind of remind ourselves, we worked with opposites when we did the inequalities. What side is opposite angle C? This one is C here. Keely? Segment AB is opposite angle C. And which angle is opposite segment BC? Joseph? Angle A, right? Okay, good. Excellent. So we know the vocabulary. Yeah? Maybe. So, good question. I'm glad you asked that. Let's see if we can figure that out. Just like I hired her. I'll pay you later, right? That was perfect. So we're going to do a real quick activity. It won't take long. I'm going to give you our snap sticks, our good friends the snap sticks, and we're going to create an isosceles triangle out of them, and then I'm going to want you to measure angles and see if we can conclude anything. And then you're going to create an equilateral triangle, measure angles, and see if we can come to any conclusions from that. So while we're collecting up our little snap sticks, our inductive conclusion, inductive, is that it appears our base angles are going to be congruent and our vertex angle is different, or is it? Right? What if we have this one? Where's the base angles? Where's the vertex angle? Yeah, what do you think? It's not an isosceles triangle? That's a good question. Is an equilateral triangle an isosceles triangle?
No.
No? What's the definition of an isosceles triangle?
A triangle with two sides.
With two sides. Notice how it doesn't say two and only two? So does this have two sides congruent? Yeah. I mean, it has three sides congruent, but if you have three sides congruent, you have two sides congruent. That's why we use those kind of one and only terms when we don't want that situation. So it is true that equilateral triangles are isosceles triangles. Now, you can turn it the other way, and we can kind of see it a few different ways. But not all isosceles triangles are equilateral. Okay, awesome. So from these, we're going to build these theorems. The base angles theorem, which says if two sides of a triangle are congruent, then the angles opposite them are congruent. And we have a converse to that, which says if you have two angles of a triangle congruent, then the opposite sides must be congruent. So, okay, what's the base angle theorem? You have an isosceles triangle. You know two sides are congruent. That means that the base angles will be congruent. The converse says, if you have a triangle and you have these two things congruent, then the sides opposite are congruent. Basically, if these two angles are congruent, you have an isosceles triangle. Yes, sir? Is this like the hinge theorem in what way? I'm not sure. Think about it a little more. And again, this is my first class I've been really loving that hinge theorem. Yes, ma'am.
All I wanted to say is I think what was going on in his mind is that picture also kind of slightly determine angle values by the side values. I mean, not precisely, but
Right. So there's some relationship between the angle and the sides. That's true. Maybe that was it. All right. So I gotta prove it, or I can't use it, can I? So I'm given a triangle, and all I know is that it's isosceles. So I'm going to say JK and JL are congruent. What I want to prove is that the base angle is congruent, angle K to angle L. So to prove this, I'm going to start by drawing a segment bisector. So what does a segment bisector do? Yeah, what does it do, Amanda?
it splits the segment into two congruent little segments.
Yes. So here comes JM. Since it's a segment bisector, these are the congruent pieces being made. If it had been an angle bisector, you could say the angles are the congruent pieces here. So let's see. Now I'm going to say that MK and ML are congruent. You know, assume my givens were already set. So why are MK and ML congruent? Definition of a segment bisector. Then I'm going to say that JK, I'm going to say JK coming into JF already. I think it's right here. JM is congruent. I want to say this one first, right? This one doesn't look right. This one, oh, given. I'm sorry. Hello, I'm here. JK is congruent to JM because it's given. And then JM is congruent to JM by with the reflexive theorem. Therefore, the triangles are congruent by, it looks like side, side, side. So angle K is congruent to angle L by CPCTC. So what we saw inductively by just kind of experimenting, we can now see deductively by facts that this is always going to be true. Yeah? Okay. Now we could have done this another way. What if we had said, get rid of some of this, that instead of knowing this part, I told you, well, we still have this part, but I'm saying that this is an angle bisector. I still could have gotten there by side angle side. So there's more than one way to prove these things. More than one way. But it's proven. I got it. We have these corollaries, and if you remember what a corollary is, it's like a theorem that you can easily prove based on another theorem. So the corollary to the base angles theorem is that if a triangle is equilateral, it is equiangular. And basically what that says is, here's my equilateral. Well, if I just look at these two sides, the base angles theorem says that this one's congruent to this one. You kind of turn your head around, and you look at these two sides, and now you've got these base angles. Turn your head around the other way. These two sides are congruent, so these angles are congruent. Oh. So we're just applying that base angles theorem a few different times, and we can come up with an equilateral is equiangular. Now we've been using this all along, but finally we're proving it, so we can use it even more. Same thing, that corollary. We're using the corollary to the base angles theorem to show that if you have equiangular, you've got equilateral. Right? So if you have these two angles, this is congruent side. If you have these two angles, then these are congruent sides, and so on. So we get all these cool things. And what is the measure of each angle in an equiangular triangle? I know you know this. Little box on the right there. What will the measures of each angle be in an equiangular triangle? Joseph, 60 degrees. And if you look on your notes there, there's a little box on kind of the rightish side. Each angle in an equiangular triangle measures 60 degrees. There it goes. Now, do the angle measures change if the side length of an equilateral triangle changes? And we talked about this as well. So now if I have bigger sides, but I still know it's equilateral,
Oh, all of them.
does that change?
Or more, if just one of them.
Well, no, but if I change all of them the same, so it's still equilateral, then it's still going to be 60, right? Always going to be 60. I guess the answer to that question is no. So each angle will always be 60 degrees if you have an equiangular or an equilateral triangle. All right, so looking at a few examples now. Example A, we're given RT is congruent to ST. Yeah, let's see if we can do this one. Name two congruent angles. Seriously? Oh, we don't want to participate. Abby?
Angle R and Y. Participation is boring.
Oh, no, it's not. Because we're using that base angle theorem. Okay? And yeah, simple one, but just to make sure we get that, we'll find the theorem right. Okay? Find the length of AB and the length of AC in the triangle at right. That will be here. Amanda?
Well, AB and AC are both 11 units.
Can you tell me why?
Because I know that the triangle is equiangular, therefore it must be equilateral because the Corollaries and others Isosceles Theorem. And since segment CB is 11 units, since it's equilateral, the other side must be equal to it.
Beautiful. That was a beautiful explanation. Perfectly explained. Okay, let's look at example C. See, we're going to raise the bar a little bit here. I'm just going to shut the door a little bit. I hear a lot of noise out there. Let's see if we can figure this out. So I want to find the length of WY and the measure of angle WXY. WY. So let's see what we know. So again, marking up the diagrams, so important. Looking around, wait.
Why don't we just put angle X?
Well, I'm looking here. I could have. This is base angles, right? So I'm going to use the converse of that theorem to know that these are congruent sides, right? If you have two congruent angles, the opposite sides are congruent. That's the converse to the base angles theorem. So if this side is 6, what is this side? Has to be 6. I think we found the answer to that question. Now we have to find the measure of WXY, which that says just the inputs. Yes, you could. What do you think? I see one hand, I see 2 hands, 3 hands. Jacob, what do you think? Tell me why. And so? Yes. And equiangular triangles, right? They're all going to be 60 degrees. Nice. All right. Let's try the next one. The measure of angle DEF is 90, so I'm going to go and mark that. Okay, putting in my right angle marker, marking up my diagram. Okay, let's see what's going on here. I want to find the values of x and y. So x is over here. Joseph, what do you think? 60. Why is x 60? Well, it's equilateral, right? So they're all going to be 60. And now what I want to find, what else do I want to find here? The y value. Jack, what do you think?
Y equals 6.
Why?
Because since the two angles of the bottom triangle are the
Okay, so
opposite
the
sides.
angle F and angle FEG are congruent, yes. Therefore,
the sides of the equilateral triangle are 3.
well, this is Isosceles, right?
Yeah, but
I just step at a time. I'm slowing you. I know you got it right. I'm slowing you down. I want you to explain it. So, since these base angles are congruent, the sides opposite are congruent. Yep. So that means this is 3. That means this is 3. But this one little tick mark, right? These are all congruent, so these are all 3. And so now, tell me the conclusion. Segment addition, right? I can say that 3 and 3 is 6.
Also,
So,
the information that is provided is on us.
well, I don't, maybe not. We never know. We never know what we're going to need. That's why I'm all about marking up a diagram, and you never know what you're going to need. We didn't really need this for, but there it is. Okay, let's try this next one here. Whoa, oh no. What congruence postulate can be used to prove triangle ABC, that's this guy, is going to be congruent to AED. That's this guy. And let's think a little bit here. What do you think, Julie? Side, 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 tell me why.
Because, since
Well, let's get, let's mark these. You got these ones, right?
there are two sides currently that are congruent.
Okay.
But since triangle ACD is equilateral because angles ACD,
Wait, which one's equilateral?
ACD, yeah.
Well, I know this one's 60. How do I know this is equilateral?
Because, they're not all equilateral triangles and it's
Well, how do I know this one's equilateral? I know this one's 60. How do I know this one's 60 and this one's 60? Wait, look at her chance. So I don't know if I know that. But I like that she's looking for these equilateral triangles, these isosceles triangles. Keely, back it up a little bit. And I want you to look at the big triangle here. ABE. What do I know about triangle ABE? Let me see here. This one and this one are the same, right? So what does that say? What kind of a triangle is ABE? When two sides are congruent, what kind of triangle is that? The ones we're learning about. Isosceles. So if you have two sides congruent, what do you know about the opposite angles? Right, these are going to be congruent. So what's this measure? So what's this measure? Why are these two triangles congruent? Side, angle, side, side, angle, side. Whoa, okay, good. Now, explain why ACD is equiangular. Oh no. Now we're getting back to this one. Why is that equiangular? I have more information now. Amanda, what do you think?
Because if you can see segments AC and AB are congruent.
Okay, wait, let it finish, yeah?
And
Great.
because of that, the base angles, one of which is equal to 60 degrees and the other one would also be because of the both congruent. And since all angles in your triangle must add up to 180 degrees,
Yep.
and we already have 120, that means we only have 60 left for the top one, so that must be congruent.
There you go. Wow, look at that. Look at that. Yes.
Kind of differently.
How'd you do it?
With the one circular measure that we were given, we let the other side of it, because the linear pair has to be, that 69,
That's 120.
180 minus, it had to be 120.
Okay.
The other one was 40, and
Yeah.
then 160, and then 20 would have to be the top one, it would be 180.
And so this one has to be 20 also?
Yeah, and since that one's coming, then you can get from that.
Oh, and then you got 40 and 40.
Yeah,
So that's 80. So this whole thing has to be 100?
yeah.
Okay. Another way to get there. Do you have another way?
You don't even need to know this triangle if you really.
I don't?
No. Since AB and AE are equivalent, that means angle BCA and ABE must be equivalent due to the converse of the base angles theorem. And therefore, since they're equivalent, they're both in a linear pair with ACD and ABC respectively. Angle ABC must equal ACD because they're a linear pair, because their supplements are equal.
Right. I think that's kind of where Evan is going, sort of-ish. Similar idea. You lost me a little bit with all the different angles there, but you were saying it didn't matter that these were congruent? Is that what you're saying?
It doesn't matter what you know they're congruent.
Okay. All right. But look at that. Look at all the different ways you got there. That is awesome. Now, what do they want me to show? ABD. Oh, goodness. I need some colors here. So, ABD, show that that one is congruent to AEC. Wow. Now, we got so much information here. Let's give everybody a little chance to think about it first. This one and this one. Can you see it already?
Yeah.
How?
Triangle ABC and ADE are reflected.
Okay, wait. Back it up. Can we go easier rather than harder? Looks like you're going for a real difficult way to kind of explain this. I'm looking for a theorem. Side, angle, side. I'm looking for a congruence theorem, if you can do it that way. What do you think, Keely?
We already know all these.
We do. So does it work? Does it match up? Like this one and this one, so we got an angle, right? We got this angle, right? That part part of the red one. We got this one, part of the blue one here, the green one. Two angles. We got a side, and we got a side. Well, three angles doesn't help us, but two of them does. And we got side, so we got everything. We could do angle, angle, side, right? We could probably get a side, side, side out of this if you kind of added in that value with that. I think we could use almost anything. Because she's like, listen, you know all the sides, you know all the angles. Absolutely. So there's all kinds of things you can do with this new theorem. Oh, how exciting. Alrighty, let's find the values of x and y on this guy. What do we got here? X and y. Oh. So we're analyzing. I see these. And I'm just marking like crazy. I'm just looking what I see. Which that means this is 60, right? Because this was equiangular, it's equilateral. And you're right, I don't necessarily know if I need all this information, but maybe I do. There's a 12, there's a 12, there's a 12. Oh wait, so that's a 12. So this is isosceles, so this one and this one are congruent. I don't know if that helps or not. See this right angle? Who else is a right angle then? This one, right? So if this piece is 60, what's this little piece in here? 30. Okay. Wait a second. These are congruent. So if that one's x, that one's x. Triangle sum theorem says it all adds up to 180, right? So that means 2x plus 30. Is that going to be 180? Can you add the angles up right? I'm going to subtract 30 from both sides. And then I'm going to divide by 2. Yeah? 75, right? Yeah, so it looks like these are 75 degrees. So the measure of angle x is 75 degrees. I think we got that. And now they want us to find y. Wow. Okay, this one's 15, this one's 12. It's a right triangle. I don't know if you're going to know. You might know how to find that one. Do you know how? I think the Pythagorean theorem might be the way to find this one. A squared plus b squared is c squared. Haven't formally learned that one yet, but we have a little bit when we did distance formula. So that means if I call this piece, I'm going to call it just z, have something to call it. So z squared plus 12 squared has to equal 15 squared. And I find sometimes these are easier. If you just solve for z, before I even do anything, I'm just going to solve this for z. I'm going to take the square root of both sides. And put this in the calculator. See if that helps. Just to make it a little bit, for me that's easier seeing it in one step. Maybe it isn't for you. So 15 squared minus 12 squared, boom, 9. So that's 9. So if I want the measure of y, I have to use segment addition to say it's 12 plus 9. 21? Yes, sir?
It's just 3 times the most basic height.
Right. Again, you're ahead of the rest of us. I know you know this stuff, so you're ahead. We're gonna learn how to do that faster. Yes.
Did Pythagoreans ever be another theorem?
I'm sure you have knowledge. He's a smart dude. Alrighty, and I think we have a couple more here. Find the values of x and y. X and y. On the back here. So I have my isosceles triangle. Now the base angle theorem says that if you have two sides congruent, the base angles are congruent, this equals that. So if x plus 7 is 55, you subtract 7 from both sides, you get, I want to say 48. So x is 48, right? Is that right? But that this whole angle, though, is 55 degrees. 55, 55. How am I going to find y? How do you find y now? You have to add up to 180, triangle sum theorem. So I'm going to say that y plus 55 plus 55 is what, 110? Is 180? Yes, so she's right. She subtracted that, so y is 70. So there we go. So you just kind of play around with these different theorems. And it wouldn't be geometry class without proof. So let's do a proof here. What do we got here? BD bisects angle. If you're bisecting an angle, you're going to get two congruent angles. So I'm bisecting ADC, so these are my two congruent angles here. That's what it means to be an angle bisector. We also know that DB is perpendicular to AC, which means that I've got some right angles here. And I want to prove that ADC is isosceles. Now before I look at what they do, I'm just going to look here. Well, I see this, automatic, right? Oh, wait a second. These two triangles, CDB and ADB are congruent, aren't they? How come? Huh? Yeah, well, this is how I'm seeing it. You might see it another way. Look at these two triangles. Are they congruent? Yes, why? Angle, side, angle. Angle, side, angle. That means that this one is congruent to that one because corresponding parts of congruent triangles are congruent. That's how I see it. Maybe you see it a different way. Which way do you see it?
You can use the third angle theorem to prove that BCA and BAC are congruent.
These two? Yeah.
And you just use the converse of the base angles theorem to do that.
Okay, we can do that too. He says that by the third angles theorem, this one is congruent to this one, therefore this side is congruent to that one. Let's see what they, whoever writes these theorems want us to do. Here's our givens, right?
They want us to take the longer and we'll take the one.
Yeah, that's usually the way. DB, perpendicular, right? There's my givens. Definition of an angle bisector is that angle 2 is now congruent to angle 1, because that's what angle bisectors do. They make congruent angles. 3 is congruent to angle 4 because for two reasons here. They're right angles by the definition of perpendicular, and all right angles are congruent. I think there's two reasons why we can say 3 is congruent to 4. DB, that's our reflection, right? And then therefore, triangle BDC is congruent to triangle BDA by angle side angle. So that's the proof that I saw. And therefore, CD is congruent to AD by CPCTC. So the triangle is isosceles by, that's the definition of an isosceles triangle, two sides are congruent. Oh, we did it. Yes, sir. No. I get most of these proofs from our textbook. Kind of like the way Jack proved it. It's kind of elegant. And I will say this. If whatever they give you, this stuff, is harder than a way you see or you see a different way, you are always welcome to write your own proof from scratch. You don't have to use this. And on tonight's homework, there is a problem on there that is crazy the way they wrote out that proof. It is much simpler if you look at it another way, and I'll show you that in a second. But are there any questions? Yeah. But
I saw something I was not going to do. Since DB bisects angle CBA, then you can conclude that angle 2 and angle 1 are congruent. Can we also conclude that CB and BA are congruent?
I don't think we can conclude that until we know the triangles are congruent. This is kind of like that proof we used before. Like once I know the triangles are congruent, I can see that those are.
No, but what do you know since it's like opening the same amount, so it's the same angle?
You guys using that hinge theorem? Wow. I guess so. We actually will have a theorem that says if you have an equilateral or an isosceles triangle and you bisect the angle, you are bisecting the segment. We just proved it. So there you go. Awesome.